So QISKIT, that's the package that we'll be using. So create a separate environment in your Anaconda and kind of install this and do all of the sort of housekeeping work. It'll probably fail a few times and all that, but you should be able to do that. It's not so difficult. And this is what we will use for our coding purposes, right? Once we do this, we will actually get into the quantum computer. Okay. So this is the package that you have to use. Clear? Everybody got this? QIS?
Yes.
Yes. On the Anaconda environment. And we'll start some work. That way I can also give some homework that you guys can actually do. Hopefully you guys are doing the stuff that I'm asking you to do. I don't know. So today we'll talk about a few topics that we need to do before we get seriously into quantum mechanics, okay? So the first topic that we'll talk about a little bit is entropy. I know some of you have some idea, some of you do not have that much of an idea. So we'll talk a little bit so that I want to bring everybody onto the same page with what do we mean with entropy, more specifically in our quantum domain. Okay. We'll talk a little bit about Hamiltonian operator or Hamiltonian mechanics. I told you, right, there is Newtonian, Lagrangian and Hamiltonian. Okay, so I talked about Lagrangian in one class. I hope you guys still remember what I talked about Lagrangian, though you don't strictly need to remember that to understand Hamiltonian. It's a little more involved. It's a little more sort of complex, but we can do that. And we will also, as part of this, get a little bit into linear algebra, something called Hermitian matrices. I don't know if you guys know about this or not. Hermitian or self-adjoint. People, I'm hearing some yeses. So people have some idea about what's a self-adjoint operator, what's a self-adjoint matrix and things like that. They don't, I'll just quickly talk about what's a Hermitian matrix. We will need this as we get along, okay, in quantum mechanics. Like I said, the next 2-3 classes after this, 2 classes, not more than 2 classes will be on quantum mechanics, okay? I'm just telling you so that you can prepare yourself. That's how that's going to work. Next 2 classes, there will be quantum mechanics, and then we will get into proper quantum computing with gates and stuff. We'll talk about the algorithms using Qiskit. Okay, so that's how how long that will go depends on how long we are all interested. So we'll kind of do that. So that's the broad idea. Anybody has anything to say about this? Wants to do something else? Maybe I'm missing something. I'm not missing something. Whatever. See, the more you keep quiet, no, the more difficult it becomes for me, and it becomes more difficult for you also, because I will just skip a lot of things.
For me, he had given up. So only hope is answered. I am only.
Okay, so I don't know. You guys are all relaxed. See, I teach classes, and I'm dying for a class where. Anyway, we'll talk about entropy. Okay. Talk about entropy. Okay, let me ask this question. What is entropy? Anybody has any idea? Yes. Where did you hear about it?
The disorder, measurement of disorder.
Correct. Let me put one thing here. Good. Wait, I'll come to you. Measurement of disorder. Yes, that is one thing that you keep hearing. What did you say?
Solid state physics.
So somewhere in solid state physics. What is solid state physics, by the way?
Not just a state where it can be.
Electronic engineers, electrical engineers. What is this? I'll have to start calling names here.
Somewhere in the car. Data scientist should be doing that word. That is
Raja is like a data scientist should be doing that. So who is a data scientist here? Well, now nobody wants to be a data scientist. No. Anyway, so Any other definition you want? Any other things about what is entropy? Guys on the call, come on, man, step up, have fun.
The amount of thermal energy present in the system.
Thermal energy. Good. So something to do with energy. Okay. Anything else? Who are all there? Now let me.
It's a measure of uncertainty, basically the
Measure of uncertainty. Yes, that's a good one. Raju, is it you?
Yes, yes.
Measurement of uncertainty. See, this is what we in all these definitions. Actually, if I get deeper, we are all digging ourselves into bigger holes because each word that you are using there. But anyway, that's good. It's good that you're at least thinking. Who else is there? Anik, do you know? Any idea? Heard about the word entropy?
Yes, I heard of it. Actually, I said that in thermodynamics, then.
Sorry? Speak up, man. I can't hear you.
In thermodynamics, I mean, it is already said that.
So when you were studying thermodynamics, you heard of entropy. Okay, good. So I think this is good, and this is partly the reason I wanted to talk about this. See, all of these are so many different definitions. Somebody thinks it's got something to do with order, disorder. Yes, in certain contexts, yes. Somebody thinks it's got something to do with heat or thermal energy and things like that, right? Measurement of heat, measurement of uncertainty. Okay, this is a very, very important word, both in machine learning and in quantum computing. Keep hearing this word. All of these are right, but all of these are wrong also. Okay, it's something more fundamental. And today we will try and understand entropy without many of these so-called, keywords. Let's just try and understand the concept. Exactly what does it mean? We'll focus on Shannon's definition of entropy. Now there are multiple definitions of entropy, right? You have Gibbs entropy, you have Shannon's entropy, you have Lipschitz entropy, you have multiple entropy measures in physics and in mathematics. But the one that we will be focused on is Shannon. Is Shannon's entropy, and we will see, though I don't know if I'll have time, I will explain, otherwise I'll leave that as homework, how this Shannon's entropy actually is related to every other type of entropy definition out there. They end up being the same value in certain conditions and not being the same value in certain conditions, but that's fine. So we'll talk about Shannon's entropy. Any people have heard about this man before? Haven't heard about Claude Shannon? So that's homework number 1. Google Claude Shannon. He is the reason why you have a laptop and a cell phone today and everything else with you. Okay, he is the one man behind most of the electronics revolution that we had. He was a professor at MIT at 1930s, 1940s. Absolute genius of a man. You should Google him at least. At least Claude Shannon is somebody that you should know a little bit. Okay, now let's try and quickly understand, at least in a basic sense, what does it mean. See, let us say you have a set, okay? Let's simply say you have a set. You have some objects in this set. Some of them are, let us say, circles, some of them are stars, some of them are triangles, okay? And some of them are squares. Let's say you have a set like this. Correct? What does entropy of the set mean? When I say there is a set of things, now you can imagine this to be anything. Thermal energy, you can imagine to be molecules. In uncertainty, you can imagine them to be different shapes. You can imagine them to be whatever you want, right? It's a set made up of different things. Here we are talking about shape, it can be anything. What does entropy mean here? What do I say when I say entropy? What am I measuring? Okay. You should think about it very simply. The best way that I have found over the years to think about entropy is entropy can be defined as the variability. And there is a reason why I did not say uncertainty here. It is the variability of the set. How different are different elements of a set from each other is what entropy measures. Okay, it measures the variability of any set. Now, I'll write a formula here, and this is just a formula. Just don't worry about it at this point. This actually comes to the entropy of the set is given by the formula. It's usually depicted by small h, and we'll discuss what each one of these things means. So don't worry right now about it. It's written in small h. In most literature, it will be small h. In some literature, you'll also see it as capital H, but largely it's written as small h. It is defined as the negative minus of the summation pi log pi, which is summation over all the elements. Okay? So you can take this as 1, 2, 3, 4, summation over all the elements. The pi and the log pi. Now I am little careful about defining pi. See, typically if I say pi is the probability. Pi is the probability of the ith element. But what does it even mean? Okay, what do you mean when I say the probability of the ith element multiplied by the log of the probability of the ith element? This is what it gives you. See, don't worry about the negative sign. Just think that, 1 by pi, see, this is actually, you can write this as sigma pi 1 by pi, log 1 by pi. When I make it pi, that's why the minus sign comes in. So the minus sign is just due to that fact. Okay, don't get confused that why is entropy negative. Entropy is not negative. Okay, you're not talking about negative entropy. The negative sign is just for the 1 by pi term. Okay, it's just the mathematical circus that you do not to get that. Okay, it's not really anything. Now, what does pi actually represent? I think most of the confusion starts right from here. What does this word pi actually represent? Before we get in there, I think I want to remove another confusion which a lot of people will have. A lot of you guys will probably talk about something is a statistical distribution, something is a probability distribution. I think we need to understand what those words are and be very, very clear with it. Because in quantum computing, that will become critical of how you understand what those different types of distributions are first. So let's first talk about this, okay? What is a statistical distribution? When I say that something follows a statistical distribution, right? It's a word that all of you have heard, right? As data scientists, mathematics students, statistics students, everybody keeps telling you, oh, normal distribution, Gaussian distribution, Poisson distribution, whatever. We call them statistical distributions, right? What is a statistical distribution actually? When I say this, what do I mean? Okay. And we will talk in the context of pi. Right? So what does pi mean in terms of a statistical distribution? Pi here just means the frequency. Right? What do I mean by frequency? The fraction of that object in the ith case, right? If you're talking about pi of triangle, it is the number of triangles by total number of objects. Right? This is how pi is defined in a statistical distribution when you talk about a statistical distribution. So basically your PIs will show you what all shapes are there and in what proportion. That is what it will give you, where sigma pi will be equal to 1 because you are normalizing this because of this normalizing constant, right? So this is what pi means in terms of a statistical distribution, correct? So the h of pi or whatever, the h of pi will basically talk about the variability in terms of what is in there in that set, right? For example, if I can say some, I don't know, 60% of of the people in this hall are women or something. Right? That is because you are actually counting the number of women by the total number of people and whatever it is, and that is what PI is depicting. Very clear, right? It's not very complicated, it's very clear. Then you, instead of statistical distribution, let us call it a probability distribution. You are now saying let this be a probability distribution and not a statistical distribution. What does PI mean here? When I say something is a probability distribution, what does PI mean in this case? It is the chance that the ith element is something, right? See, there's a subtle difference between both. You have to be very careful. The first thing I said, it just is the frequency of things in it. The second one is not that. When I say that this is a probability distribution, I mean, what is PI of triangle? Is what is the chance that if you randomly pick something up, it will end up being a triangle, which in under certain assumptions will be the same as the PI in a statistical distribution, but not necessarily. Not necessarily. If you're saying you're doing it, for example, without replacement, if you're saying all of them have equal chance, if you're making those assumptions, then these two PIs will be equal, but not necessary. And I cannot tell you how many people get confused here. Okay. This is a probability. Not all statistical distributions are probability distributions. Yeah. In case this is a probability distribution, this is what it is. Guys on the phone, is it getting clear? Will be.
Yes, sir.
Yes, Srini.
Yes. Okay. Good. Because this is so. What is H measuring here? The variability of what could turn up, right? If you pick up, that is what the H is measuring in a probability distribution. In a statistical distribution, it is measuring the probability of something. Here it is measuring of something coming up. It's a probability distribution. It's a probability. It's a belief. It's chance, right? Again, those are all difficult words in probability theory. Each one of what I've said is a semester's worth of class. But think about it right now like that, okay? And when I say probability, again, for people who are interested, just go and look up Kolmogorov's definition. I know I talked about it, but just go look up it once. Because every time I say probability in this class and in all classes, Srinivas Atreya will only talk about Kolmogorov's definition of probability. If I'm talking about some other definition of probability, I'll be clear. I'll tell you that today, guys, I'm talking about some other definition of probability, right? Kolmogorov is our man. Now, there is a third type of distribution also, which is probably the most important one if you're a machine learning engineer, right?
Combination of both.
Yes, we will get into combinations of both. we will get into combinations of all three actually. But first, let us individually understand what those three are, and then I will combine them in maths, okay? The third is called credence distribution. Okay? So what is the credence distribution? Credence distribution is basically the belief that you have that something is something. Right? Here the PI represents the belief that ith is something. So given that it will be something. So the other one, it just represents the probability. This represents the belief that something is something. So for example, if you say, I have 66% confidence that 30% of the women are 30% of the people are women, then that I have a 66% belief is the credence, is the interval, confidence interval. I have a 95% confidence that is that. So that 95% probability is your credence PI, because you are putting an uncertainty bound. You are putting your belief, saying that I am 99% confident that the average height of men in India is between 5.4 and 5.6 inches. If I make this statement, the fact that you have X percentage confidence in that measurement is a credence distribution in itself. If you plot that itself will end up being a distribution of some random variable, the random variable being the confidence interval.
Is there some mathematical base to it, or it is used for
just
a calculation?
No.
I go for, say, probability distribution, and I want to apply credence distribution on top of it.
You will. Exactly. You will do that.
Belief on this probability distribution working is this.
Based on some statistical distribution.
Again.
Based on some statistics. Given that 45% of India's population are women, what I have 99% confidence that whatever 80% of the people in this are this, if you say that. So given that is a statistical distribution.
Yes.
Okay, so that initial thing that you're talking about is the statistical distribution. Then you are saying that I have 99% confidence, a credence distribution. I have 80% of it will be women is the probability distribution. So essentially you're mixing all three. Okay, and that is how most statements go around probability when you talk about it. But you have to understand that it is made up of three different things. There is a credence part of it, the credibility or the confidence interval part of it. Then there is the actual based on some distribution which you believe in, some statistical distribution that exists. You are estimating a probability. So all three of them together, and all of them unfortunately in our world are called PIs only. All of them we call probability only. Okay? Because all of them follow those Kolmogorov's laws. Because all that Kolmogorov did was very simple, right? He said anything is a probability as long as PI is greater than 0. Okay, everything is a probability as long as the probability of a certain event is 1. And if there are two disjoint events, the probability is of P1, probability of event 1, union E2, if they are independent, is probability of E1 plus probability of event E2. These are the three laws that Kolmogorov put in. He said any number that satisfies these three laws is a probability. That's all. He took all philosophy out of it. There is no philosophy. He just said three laws, 1, 2, 3. And all of these PIs will follow these 1, 2, 3 laws. So hence we are saying everything is a probability. But it is important to understand that there are all different types of probabilities. And what we are measuring and calculating there when we say PIs are very, very different. That's very, very important. Especially when you start getting into entanglement and things like that, it will get critical to understand what these things mean, right? Yeah, I spoke a lot. I hope 20% of it has gone. Okay. If not anything, remember that there are three types of distributions and three types of PIs. When I say PI, in your mind, in the initial days, train yourself to think what PI is this. You do that for a few years, you will automatically get to understand, he's talking about a credence probability. Okay. That makes your own understanding of probability much, much clearer. Probability is one of those tricky areas that looks like it's very easy. Something happened. I don't know. Oh, my Google, for some reasons, started thinking I'm talking to it. Okay, that's fine. I'm not talking to Google at this point. See, this is what happens when you do too much of stupid machine learning programming without understanding. So anyway, so this is what this is, right? Okay. Everybody on the audience, now we're going to get into a little more detail and talk about what is exactly, going to talk a little bit more about it, but everybody clear? And people in machine learning would know that most of the time in machine learning, we're talking about credence distributions only, right? Because we are just saying if you have to classify this as a dog, what is the question you're asking? I am 95% confident that this thing is a dog. Well, what is that probability? That's a credence distribution. Okay. If you have not understood that from till now, so at least today you've learned one new thing. At least people who work with machine learning. Okay. Some response, guys. For all of this vocal energy I'm spending, you can also spend some. It's okay.
Sure.
Yes, yeah. Correct.
So very difficult to teach online, man. I'm telling you. Because you never know if people have put you on mute and gone somewhere, you're just talking to an empty set of people, or even listening to what you're trying to say.
Brains are actually processing the information.
Yeah, process it, no problem.
Sometimes they just leave. I don't have any confidence. I'm just depending
Yeah,
on.
in which case you won't really say it. But yes, in theory, yes, I have 0%. See, even when you say you have 0% confidence, that means you know something. See, if you don't know anything, you will say, I think 50%. If it is a binary, if it is binary, 50% means that you know nothing. 0% means you know a lot.
I'm confident.
You are very confident that it is not, right? 0. So how do you know that? So actually 0% and 100% are of equal confidence. 50% is the most useless thing. And if it's a binary thing, you know, that's the trick that most godmen play, right? The trick that most godmen play is that, see, they understand probability inequality is better than most of us. The expectation of a random variable is the average.
Yes.
So if you keep saying, giving the average answer, you will get it right more number of times when n tends to a large number. So if you have a lot of luck, you will succeed. You will have to succeed. There is no other way. You cannot fail. There is a very nice mathematical theory. It's called the mean reversion theory. Which says things will revert back to the mean, the expectation.
Yes.
It's the mean reversion theory. It's used everywhere. It's used right from gamblers to stock market trading to anything and everything that you talk about is called mean reversion theory. It's actually a guy called Francis Dalton. You should probably read about him. Okay, it's called. That's the whole thing. Why KBC's wisdom of what is that? The whole audience polls, and the answer is right most of the time. Why is it right? Why is that a good strategy? It's a good strategy because wisdom of the crowds. Yeah, mean reversion theory. Wisdom of the crowds. Some will cancel this way, that way. Finally, the answer will be the mean, which most of the time anyway ends up being the right answer. There was a question. One of my professors back when I was in NIT Trichy, she asked me. She was a brilliant professor actually. She asked me, or not me, the entire class. The question was, how many piano repairers are there in Chennai? Yes. With absolutely no background given. You just have to assume. Assume the population is this much. Assume this is this. It's not how many. It's basically what ratio, what percentage of Chennai's population are piano repairers. And then you make all assumptions. Yeah. This way, that way, that way. They all finally the proportion you will more or less end up at the correct. If your assumptions are sort of commonsensical, you will get to the right answer without knowing anything about anything.
Usually they ask this question for anything. How many Western?
Anything.
How many?
Anything. You can ask this question. And you will get the right answer irrespective of you knowing nothing about anything else. Okay? It's a beautiful mathematical theory. You'll always get the right answer. You will. You are bound to. And that's why mathematics is not just abstract. There are a lot of fun things you can do. There's actually a problem called a secretary problem, which you probably guys know about it. Secretary problem, or it's also famously called the Gaussian marriage problem. You know what is the problem? Maybe you guys should do this. This is a homework. It's a good one. I'm going to give a fun example. I'm going to say, probably you're trying to get married, let's just say. Let's just say you're a guy or a girl who's trying to get married. So how many people should you reject before you are confident of meeting the right person?
None.
Solve it. There is a mathematical answer to this.
None, because I choose the first one.
It is not a very optimal strategy. Okay. That is not an optimal strategy.
Maybe the compensate the other side.
Yeah,
What
you
happens
rejected
sometimes.
Samir rejected 6 people, I rejected 2.
And the same is not the secretary problem. If you are hiring for a role for a secretary, how many secretaries should you actually decline before deciding on one? Okay, and you'll be surprised. There is a very, very clear mathematical answer to this. But I'll give you the answer. The answer is 37%. If you want to see, if you decide to see 100 girls or 100 boys, first 37 that you see, never fall for them. From the 38th, whichever one you find that is suiting your thing, agree. That will be the most optimal answer. And you can prove this. I can prove it to you very, very clear mathematically saying that this is the answer. So mathematics is not just for fun. You can do many useful things also. Same thing, you're trying to do stock trading, you're trying to do anything, people do this. People do this.
The first round of interviews in colleges, they're elimination.
They eliminate because it tells you this very clearly. But of course, this assumes certain things. This assumes that once you reject somebody, they're not available for you and things like that. Some basic. If they're again available, then the math becomes a little complex. But you can still solve it, and it was solved by Gauss. Frederick Gauss solved it. Okay.
Maybe because we have so many options, that's why we are going to that percentage. If we don't have any options, we have to stick with one.
That is
that is a trivial answer. No, if you don't have any other, what do you do? Anyway, there is no option. Then what mathematics can give you a solution. It cannot create girls for you or boys for someone. Sorry. Anyway, sorry guys. Let's not diverse.
So it's basically as n tends to the greater number, eventually end up with some Euler number.
Yes, exactly. You see, if you have sat in a maths class for an hour and if they haven't talked about Euler, Gauss, Laplace or Lagrange, walk out of the class. Because basically they are not telling you anything useful. 1 hour if you sit in a maths class, these 4 or 5 people you have to hear. Because without them there is no modern math actually. Now, but see, here is the big problem, right? Now I talked about variability. I said this talks about variability. Now somebody may question, we already have variance.
Initial thought I had was that, yeah.
Good thought, Dheeraj. So why bother with one more metric? If variability measures this, what does variance measure? Correct? What is the variance of x? Is expectation of x minus x bar square. Correct? If you rewrite it, it is basically sigma pi xi minus x bar square, right? Expectation. I'm just rewriting expectation. Okay. So what is this measuring, and what is this measuring, and why do we have another thing called variability, which I'm calling entropy? It's an interesting way to think, no? So tell me, I think this is an old friend of most people. You cannot avoid variance. So what do you think variance is measuring? What is this measuring? Is it really measuring the variability? Or what is it measuring?
Maybe the difference between the two variabilities is probably.
See, x bar is the average of whatever those random variables are. If they are all shapes that I've shown you, it is an average shape. If it's a height, it's an average height. If it is something else, I don't know. Of all the text written by Shakespeare, it is the average text written by Shakespeare. This actually, first there's a couple of problems. This actually measures something called spread. When is spread equal to variability and when is spread not equal to variability, right? Spread. It also sounds like variability, right? How much of variability is there? How much of variability is there? There are two basic problems with this, okay? If you understand. One, in case of non-numeric things, this average usually is a very, very contrived thing. And it doesn't make sense in a lot of cases. For example, in the case that we talked about, what is the average shape? There is nothing like an average shape here. You have to make something up. You have to just mathematically create some nonsense. Okay, you have to create, which is not really a good thing, because it is not always useful. It is useful when there are strictly numerical quantities where the average of those numerical quantities also makes sense. So then it makes, otherwise, so this is kind of restricted variance in that sense, okay? Entropy is a much wider, broader term that you can use. So that's one big difference. But the bigger difference is, now let us say there are two cases, okay, where let us say probability x equals 0 equals 99% and probability x equals 1 equals 1%. Let us say there's a distribution like this, okay? Let us say there's another distribution which says probability x equals 0 is 99% and probability x equals 100 is 1%. Now the variability between both of these distributions is same. Right? Their variability is the same, right? Because they have difference in the same. But if you calculate the variance, it will be different because of this formula, no? You understand what I'm saying here?
In variance, what the elements are is.
Yes, it is the actual values of these get important. Okay. Whereas here, because in variability, we are not really bothered. We are really just bothered about the differences. How different are different things. So variance in both of these cases will give you two different values, whereas entropy will give you the same value. Yeah. Which measures the variability. Is this sort of clear why we don't use variance in a lot of, because in quantum computing we will largely not use variance. Most of the time we will.
In customer segmentation problems and all, if we take humans as humans, then
variability makes more sense, and that is why now you brought up a very good point. See, when you write, and again it's a 2-minute digression, but you got to understand one thing. A lot of so-called models that we write in machine learning today, especially today, unfortunately, are statistical models, where you are trying to kind of discriminate between classes based on some statistical property, whatever that property is. Okay, some average, some median, some movement, okay, some statistical. But if you historically look at this field of AI, even back in 70s and 80s, a lot of them used to be physics inspired. They used to be energy based. So you are trying to discriminate between two things based on what you call their energy levels or their energy calculations. Okay. And there you use entropy, not variance based, not statistical based, energy based models. And they're coming back again. Actually, right now, if you look at some of the cutting edge technology, it's physics enabled neural networks, energy based modeling. Those things are coming back. The reason being, entropy is a far more robust indicator of variability than something like variance. Okay. Variance is a statistical measure of variability, just statistical. Statistical measures are useful, provided that's why I keep saying you can use anything. You can use anything. Okay. You can use variance. You can use some unbiased estimator of variance. You can use standard deviation. You use whatever. But you have to clearly understand the assumptions and the implications behind using them. See, statistics is all about rigor. The problem today is people are using statistics like generally for fun, Okay, answer is not coming by mean, we'll do median. Oh, answer is not coming by mean, let's take an arithmetic mean of mean and median. can do whatever, but there are implications when you do those things, right? Why are you using arithmetic mean? Why not geometric mean? Why not harmonic mean? Why is harmonic mean not valid here? Until and unless in your head you can understand those basic concepts, this will always look like voodoo only. Like some magic. Srini told us to use mean. Srini, it doesn't matter. Okay, what I tell you means nothing. It has to be. See, the first thing in science is if somebody tells you trust me, never trust him. Because there is no trust me. You have to clearly see the math behind it. It has to work. And only what trust is there? That is why I am so much paranoid of a lot of science being published today. Papers are like, trust me, I have done this. No. Why should I trust you? I don't trust you. There is no trust at all. If I would have trust you, I would have gone to a guardman, no? I would have trusted him and Athan Vibhuti is the panay. Point is, the equations have to work. The math has to work, and you have to be very, very clear about it in your head. Not clear? Spend. And another thing is, don't put yourself under time pressure. See, this is not the problem with a lot of people learning is they think I have to do this by next 2 hours because of that exam mode that we have been brought up into. Okay, next 2 hours I have to finish probability. No, you don't have to finish probability in any hours. And next journal is also okay. Do it as long as, but till you understand. Till you understand what you are getting. Okay. So, and maybe I sometimes speak in hyperbole, but what I'm essentially trying to tell you is don't put, these things are not easy. For me to understand this simple thing, variability, whatever I'm telling you is in no textbook. This is just something that I have thought about it for years and years, and then I thought, okay, this is what makes sense maybe. That's all that there is. Right? It's not like nobody taught me, but people who taught me well. They explained what entropy was to. Clearly, without all those words, it measures disorder, it measures what disorder, what order it is. It is not measuring any of those. It is measuring in any given set the variability. That's all that it's measuring. Yes, in certain cases, that can equal disorder in a system. Agreed. But you are not measuring disorder in a system. What if I gave you that set? If I said measure entropy minus sigma log pi log pi, what disorder is it measuring? You're not measuring any disorder, no? Essentially, what it is measuring there is, yes, you can say disorder because you can say if you leave those objects spontaneously, they will not mix and become one. Understand what I'm saying? If you have a block which has triangles and circles and things like that, let's say you have that rubber strip, you can take each one of them, right? You can create those out of them. Will they spontaneously become the sheet again? No. Why won't they become? Because the variability among them is such that there is no energy in the system to reverse that reaction. That is why it measures chaos or disorder. It doesn't measure disorder, but what it measures leads you to understand disorder. And that's why a cup breaks, a broken cup doesn't become one. Okay. Hence,
it's the state of the system, right? Entropy is the state of the system.
Entropy can be defined as a state of a system which measures the variability, that is why absolute zero, the entropy is zero. Because nothing moves, everything is like just there, right? So, okay, so at least conceptually, I hope after all of this time you have got something in it. Maybe let me see if I can do a mathematical derivation. What's the time? Or maybe I will do it in the next period, I don't know. I have still got some time. Okay. Now let us go to Shannon's entropy. So we have got an idea about entropy. Let us go to Shannon's entropy. I won't get into too much details because if I go then I think this will probably take another 2 hours. But Shannon's entropy is a part of information theory. Okay. This in itself is a large theory. We will not get into all of that. But, so what is this? What did this guy solve for actually? This guy solved for a simple theorem, which is, see, today we take it for granted, right? You have a pipe in which you have information flowing. When I say information flowing, what is it? Largely electrons that are kind of moving in a pipe, some electrical twisted copper cable. Okay, this is actually moving. So the idea is, how much information can be sent through some pipe of X capacity, of some capacity, guaranteeing some SLAs. So for example, if I say 99.99999% reliability. See, today if I send you an email and if you get a wrong email, how pissed will you be? WhatsApp message, you never get it wrong actually. Okay. But why don't you get it wrong? It's only an electron flip, no? It's a 0, 1. Why can't it just become 1, 0 can become 1 or 1, 1 can become 0? And your whole thing, you are making cell phone calls, you are calling somebody, I'm calling somebody good, he may hear it as an abuse, no? But he doesn't. He hears it the way I say it. Why does it happen? Right? There is no reason for it to happen. Normally, you and I in our life, we do so many mistakes just walking around this, but somehow this whole thing works so brilliantly. Flawlessly, nearly flawlessly it works. Okay, why does it work like that? There is no reason for it to work like that, right? You have to engineer that sort of solution. Typically, what will you say? Typically, if without knowing anything, if I tell you I have to send one bit, okay, 0 or 1, okay, and if this always has to be, it never should go wrong. For example, if you say this, if this is the requirement you give me, I'll send one bit. Kabhi galat nahi hona chahiye. It should always be. Thanks. So it should always be 0 or 1. So what will you say? You will send another bit also with it. Okay. Probably AND it or OR it with this. So that if at least one goes wrong. With this going wrong, send another bit. Send another bit. So some n level of redundancy you will build. If I say 100%, you will build literally infinite redundancy. Right? That is the normal. If you ask a normal person, this is the solution. How do you guarantee that this 0, this 1 never flips in your life? However you say. But we are able to do that not with infinite bits, redundant bits, no, very, very finite, limited bits, and that too so much information we are able to flow. That is because Shannon gave us an idea of something called Shannon's entropy, which tells you how many bits you need to encode a particular piece of information with high reliability. Okay, so that is what is Shannon's entropy. That the logic of it, and again, extremely critical in quantum computing. All that we do in quantum computing is actually use Shannon's theory. Okay, that's how your qubits will finally work. Though in the introductory session, I just generally said qubit 0, 1, but it's not generally qubit 0, 1, right? How does that happen? Okay, now we'll try to understand what this means actually. So now, let us look at the same previous diagram. Okay, where you have some triangles, some stars, right? Some circles, some squares probably, right? Something like this, okay? And if I ask you now a simple question on this, how many questions should you ask at the minimum to determine if something is a circle? You understand my question here? You have 3 circles, let's say, out of a total of what? 2 plus 3, 5, 7, 10, 12 things. So there are some 12 things, of which 3 are circles. Right? Now, if I ask you, what is the minimum number of questions that you should ask to find out if the shape of an object in it is a circle or not? Similarly, what is the minimum? You don't have to solve it. We will solve it, don't worry. But you don't have to solve it in your head right now. I'm just trying to put a question there. For some people who may be able to solve, it's not that difficult also, but that's fine. What is the minimum number of questions required to find out if it's a star or not? At least conceptually, you understand that the number of questions required to find out if it's a star or not is less than the number of questions that you have to ask to find out if something is a circle or not, or a triangle or not. At least that, are you able to intuitively grasp out of this? Why? Because there are more stars. Simple, at least at a very, very high level. So the variability can be written as proportional to the number of questions. Guys on the phone, making sense whatever I'm saying?
Yes, Srini.
And here I'm assuming they're all yes/no answers. They can be more also. Here they're just saying, is it a circle? Yes, no. Is it a star? Yes, no. If there are more responses there, then it will accordingly change. But that's fine. That's not the thing. Okay, I'm expecting binary responses. Okay, so that's something that you should be clear. So basically, you're doing what? N, Y, N questions, right? You have to ask some N yes/no questions to actually solve. Now, if you have C classes, okay, I'll actually move this. So we will understand this a little better. Maybe I think it will take maybe more classes than what I thought. It's already 12 o'clock. So guys, people have another 5-10 minutes. I at least want to finish entropy today.
Yes, Srini.
Yes, sir.
Okay. So if the number of classes is C, what is the number of classes here? Here C is 4, right? There are triangles, stars, circles, and squares. Here C is 4. But typically I'm saying let C be the number of different classes in that set. Then C will be less than equal to 2 power n questions, right? Because at the minimum. Because each question is yes, no, yes, no, yes, no. So n is greater than. Correct? Just taken a log here. Okay, just taken a log at base 2. Yeah. Now, what is the probability of any particular object? Probability distribution 1 by C, the number of classes of that class. Correct? So now you can derive it. What? N equals, now you can say N equals log 2C greater than chodo. The minimum is equals because it is N is greater than equal to. So equals log 2 1 by P minus so for each class, this gives you the most efficient. For each class, log 2 pi, right? For each class, this will give you. Now, if you take an average expectation of this, what is it? Pi log 2 pi. Probability summation that gives you entropy, Shannon's, and that gives you the same, right? Of course, you can change the base to anything that you want, but that is just log b of x divided by log a of x. You can change it to whatever base you want, log. Okay, but you see, it's actually as simple as this. See, this is why. See, this is the simplest derivation. Actually, if you read Shannon's original paper, it's a very, very complex derivation that he kind of does to arrive at the same point. But we don't see that is the advantage of thinking at it from variability perspective. His original derivation is not on variability. He derives entropy from energies, first principles of energy. That is how he derives it, which is also the right way to define it because that is really the most universal way of deriving it. This is just something that a long time ago, somebody that I used to work with at IASC told me, you don't need to worry that much. You can actually do it far more simply. Yeah, you don't really need to get into. I think he's probably not teaching. Professor Sheshadri, you can look him up at IASC. He's a fascinating person. Okay. He's an absolutely fascinating person. He spent all his life doing some of these things, and he's very, very good. He's doing some good work, which I'll probably share with you at some point. He takes all of these very, very important papers and writes them in very simple ways for people to understand and things like that. He does good work. See, people like that are just generally God's gift. Okay, they don't care. But anyway, I think so. So this is fine, right? I think there is one thing I wanted to do, one example I wanted to solve. If you guys have time, 5 minutes, I'll solve one example for you so that I'll bring all of this together so that we can be done with entropy. Then we will have to, next class, I think this is useful that we did entropy. Next, we will do Hamiltonian, probably on Thursday. Okay, I'll ask her to schedule it on Thursday because I wanted to do both today, but maybe I was too ambitious. So let me do Hamiltonian and Hermitian tomorrow. At least dekhte hain kaisa hota hai. Okay. I don't know. The point is not, see, literally, I just wanted to draw a table and solve this for you. This is called Hoffman's encoding. Okay, this is very important. This is actually a practical application of Shannon's entropy. Okay. This yesterday night I worked on it. Let's talk about some animal, some statistics about that animal. Number of questions, then answers, and here comes the encoding. Right? Okay, so if you have that, let's just say, what is it? There is a dog. Let me write all the animals first. Cat, fish, bird. Maybe you got to increase this a little bit more. Maybe this is too much. And then we can call something like what? Small mammal. And reptile. Let's say these are all the animals in a set. And let us say the statistics are something like this: 27%, 48%, 10%, 8%, 4%, and 3%. This adds up to 100%. So now let us say you need the number of questions, the minimum number of questions, okay, to understand these classes. Right? So first one, what will you ask, logically speaking? Correct, because close to 50%. So every time you keep splitting 50%, see, whenever you have a binary classification, the strategy is very simple. Keep dividing it where into 50-50. Because 50-50 is the best you can get. No? If there is any binary, if each thing had 3 answers, you could have done 33. 4 answers for each, then 25. But 2 answers, that's why I said I'm doing the binary sample, but you can extend it to whatever. Then instead of log 2c, it becomes whatever. So first question you will ask is it a cat? Right. Let's say there is a no and there is a y. If there is a y, it is simple. Cat and you're done. Correct? Cat is number of questions is 1. Right? The first answer is y, encoding is 1. You will get the answer right there and there. If it's a cat with 1 question, you can get it. Correct? Now what will you ask? Out of the remaining 50, 27 is close, no? To again 50-50 because you've got 50 left, 25-25. So 27 you will ask. Correct? So next question you will ask is dog. Correct? Again, if it is y, dog. If it is no, you have another chain. So what is the number of questions for dog is 2. The answer is ny. Correct? So first one has to be no, second 0, 1. Correct? That is the encoding. You need 2 bits to encode dog. Correct? After that, what?
Fish.
You have fish and reptile. You have fish, bird, small. So rest remaining is what? some 25% is remaining. Okay, so you want to do 13. You do fish and reptile together. That becomes 13. Close to 50 again, right? You are doing, so you will ask fish or reptile. Okay. The answer again is y is n. If the answer is again y, then you will say,
Fish,
is it fish? Correct. Again, y, you get whatever, fish. Correct. So how many questions do you need? You need 4 questions. Correct. So n y is what you will get, right? You'll get 0, 0, 1, 1 is your encoding for your fish. Reptile also, if fish, if it is no, it is clearly reptile here. Reptile also you will get 4. You will get what? No, 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 y.
No,
Yes,
yes.
yes, yeah.
Yes,
Yes, no.
Yes. So 0, 0, 1, 0. You can do for the others. For everything also the answer will be 4 only. And you can calculate this. This actually comes down to your Shannon's entropy only. So this is called Hoffman's encoding system. This is how bits are encoded. So when your language is encoded, it's exactly encoded like this. You know how they do it? For example, the ovals, the word E is probably occurs 12% of the time, maximum number of times. So the encoding for E will be like that. This is called the Hoffman's encoding. This is how you actually encode text or encode video or encode audio. And of course, there are many improvements to Hoffman's encoding right now. We don't use this is the raw Hoffman's encoding. There are many, many improvements to this, but that's okay. That's not something we need to, because this is not a EC class. At some electronics and communications class, they would have gone through this. Digital signal processing. Anybody studied DSP? DSP would definitely have this. In that class, Professor paper plane feed guy. But I also did the same thing. It's okay. But I didn't study electronics, but whatever. So yeah. You studied electronics, is it? Every time I say electronics, you get excited. Electronics, huh? EC. Samir is a good student. I've sat in the class. First bench, and I've sat and listened to the professor. Anyway, guys on the phone, is it making sense? What is Hoffman's encoding?
Yes, Srinivas.
This is very important because in quantum computing, this is how you will combine bits, qubits. This is how you will combine qubits when you have to send some information. You will use a variant of Hoffman's encoding, but the base is the same. So how do you entangle qubits? This is how you will entangle qubits. This is how you will entangle qubits when you are doing writing actual quantum algorithms. Okay, so I'm just giving you all of this background information to actually get there. We still have to do Hamiltonian operator. We also have to do what is a Hermitian matrix. I would suggest read about it. Okay, if you have doubts about Hermitian, Raju or somebody, you guys, you know what's a self-adjoint operator?
Yes, Srinivas.
So maybe you can tell everybody. You
Yeah,
want
sure.
to know?
I'll no, not now, but I'll send out the resources so that they can go through them.
Okay. So maybe you can do that. So Hermitian is just self-adjoint in the complex space, vector space. In the real vector space, it is called self-adjoint operator. In the complex vector space, it's called Hermitian matrix. And if you have some doubts, ask me. I'll tell you.
Yeah, in terms of linear algebra, they can also think about like conjugate transpose of matrix.
Yes. Yeah, that's what. See, because conjugate is not something that you have in the real world, right? Complex conjugate is a complex number phenomena, right? X plus iy, x minus iy, x plus iy conjugate, complex conjugate. I talked about it, right? Complex conjugate is this. You don't have a real scenario for this. So a self-adjoint operator with the additional property of complex conjugation becomes Hermitian, but that's fine. That's something that you can just go through it. Otherwise, next class I'll talk about it. That's fine. First, though, I will talk about Hamiltonian because that's way more important. Hamiltonian operator is definitely important. Now that you know entropy, hopefully you'll understand Hamiltonian operator a little better and revise Lagrangian once before you come, so that again, yeah, I shouldn't be confused when I'm writing F equals ma when I'm in a Lagrangian. Why are you doing this? I'm doing this because there's a Lagrangian operator, and then you get to the Hamiltonian operator, and then, like I said, 4 physics was Newtonian, Lagrangian, Hamiltonian, quantum. Okay. Unfortunately, people do Newtonian, they straight jump into quantum, but you should do the other 2 also. Not in detail. Detail will be in physics classes, but okay. Thank you. Hope it was useful and happy learning.